Hello, everyone. It's really nice to see you here at our beautiful new office. My name is Baidina. I'm a technical leader of the voice team here in Revolut. And today I'm going to talk about the dialogue management in voice agents. So I want this tech talk to be very practical, showcasing a real hands-on experience. But at the same time, by the end of this tech talk, I want you to have this nice and satisfying feeling of, yeah, now I know something more about voice technologies. Thanks, Anna. I appreciate that. So yeah, let's kick off. And first of all, let's listen how Revolut Voice Assistant works. And this is the real protocol that I had yesterday.
Hello, Anna. I'm Revolut Voice Assistant. This call is being recorded for quality purposes. How are you doing today?
Hey, I'm great. How are you?
I'm doing well. Thank you for asking. I'm here to help you with any questions or issues you might have about Revolut. How can I assist you today?
Well, I want to buy a beer for all 150 people that I'm seeing right now. Could you help me?
I understand. To check if I can help, are you interested in how Revolut can assist with the financial side of buying beer for 150 people?
Yes, please.
Let me see what I can find for you. Revolut offers a couple of ways to manage shared costs. You can use the split bill feature to split the cost with your contacts, or you can create a group bills to manage shared expenses with friends, even those who don't have a Revolut account. Would you like me to guide you through the steps for either of these options?
No, thank you.
Happy to help. Feel free to reach out if anything else comes up. Thanks for contacting us and have a great day.
Well, that was it. This is how it looks like at the moment. So where and how did we launch our voice assistant? Currently, voice assistant is live in more than 20 countries, including almost all Europe and UK. And we are having more than 25K calls a month. And in terms of business impact, we can see an 8 times lower resolution time versus if we just route all calls to a live agent, meaning our customers got their answers sooner. And we started as a vendor-based solution, and we launched together with our dearest partners, Lemon Labs, who are also here today. Guys, we're the best. And currently, we are live with our own in-house pipeline. So yeah, let's briefly look under the hood of what's going on inside the voice assistant. You can think of it as an event-driven state machine, which moves through listening, thinking, and speaking state based on different events like, okay, I can hear the user started speaking, I need to listen. Okay, the user has ended speaking, I need to think about the response, and so on. And basically, we orchestrate speech-to-text, LLM, and text-to-speech models using advanced dialogue management techniques, and we do it in real time to ensure that we have all responses P50 latency in less than 2 seconds. So that's how we make it really conversational and human-like. So the great question is, how do we make those answers from the voice assistant to be meaningful? How do we make them make sense? And as you may know, Revolut have already a big and great product, which is Chatbot, which is working really great. It's LLM based. And first natural idea was, okay, let's reuse it. Let's make our Chatbot talk and put it inside our voice assistant as the main LLM. But voice and text domains, they are really different. And a few extra seconds of latency in the text domain, it's completely fine. And if you add few seconds of latency inside the voice domain, then you get a ruined conversation and everything is just really bad. So that's why we came up with the architecture that you can see here. Basically, we utilize a separate LLM and we do a to call to the Chatbot API, and then we retrieve the information, and based on that, we provide all the answers, preserving the nice latency. Here, I wanted to share some important insights. Even if you have a perfect speech-to-text, LLM, and text-to-speech models, it's just not enough to build the great conversational experience without the dialogue management. So this is the key, the secret ingredient that you use to make the assistant really the human and talk to you nice. So what is those dialogue management techniques? Basically, dialogue management is a conversation control layer which decides should assistant speak or should it listen. And we can imagine if speech-to-text is ears, LLM is a brain, and speech-to-text is text-to-speech is a mouth, then dialogue management is kind of personality of your assistant. So it defines how it behaves. Like, is it interruptive? Does assistant response make sense and it replied to the right question or so? Or is it very slow and unresponsive and so on? When dialogue management works, it just feels natural and absolutely fine. But if it doesn't work, then you get this classic voice bot vibe when you just want to, like, you're begging for a live agent and you want to end this all. So that's why it's really important. Let's take a look at the picture where I try to illustrate how dialogue management improves the experience. First of all, the conversation without the dialogue management. Here we can see that the user started the phrase when I try to make a purchase, and the end of the question was like with a small delay, and it was like, it is declined. Without the dialogue management, voice assistant decided, okay, the first part is ended, I need to answer. And it rushed into the premature response, which basically was like, it didn't make sense. It answered like, okay, make a purchase. What can I find for you? But in reality, it was like a wrong move. And it should have listened to the second part of the speech. And if we take a look at the conversation with the dialogue management, the assistant understood, okay, this pause inside the question is just a pause. It's not the end of the turn. Let's listen until the end, and only then we provide the answer, the correctly timed answer, and the answer that really makes sense. And by the way, without the dialogue management, LLM and voice assistant, they just almost interrupted the user, which was really not nice. Okay, and before we dive deeper into the dialogue management techniques, let's first revise some voice technologies basics that will help us to do that, starting from the spectrogram concept. So what it is. Basically, spectrogram is a two-dimensional representation of sound. Left to right, it's time, bottom to top is frequency, and the color in the picture represents the energy, like this, how strong each frequency is. And the brighter color means more energy, darker means little. How do we obtain this picture? Okay, we take the raw audio waveform, then we cut it into the small overlapping windows. Then for each window, we apply fast Fourier transform, and then we stack them over time. And then we obtain this beautiful picture. But can we really see a speech on the spectrogram? The answer is yes, we can. Basically, a speech is a set of vowels and consonants which are blended into each other smoothly. And the vowels are made by the vibrations of your vocal cords, and it's strong and like smooth. And in the spectrogram, they are usually represented like that. Bright waves in the lower frequency area. On the other hand, the consonants, how are they made? You just block the airflow with your mouth movements, and that's why consonants are located in the higher frequencies area, and it's like a burst, subtle burst. And you can ask me, like, what is the noise then? A noise, like, there are a lot of different noises, of course, but usually noise has a constant shape, and it's like a spray all over some frequency on the spectrogram. So yeah, if we can visually distinguish the speech from just noise or just silence, then for sure we can create an algorithm that can help us to do that automatically. And these algorithms, they are called voice activity detectors. So here I want to spend a bit of time to look into those algorithms, because from my experience, a lot of people just use them because it's like very easy to find, very easy to utilize and introduce into the production system, but nobody really cares how do they work, and nobody knows how they work under the hood. So what is like these voice activity detectors? Basically, this is the algorithm which predicts if there is a speech versus if there is a silence at each moment of time. And we can start looking into it by the simplest algorithm out there, which is energy-based VAD. And the idea is super simple. You take the spectrogram and then you focus on the white area, which is representing the area of human voice frequencies. Like this area is common for human voice. And then you just calculate the energy inside this box, and then you apply some heuristics, then you do some temporal smooth, and then you get the probability for each moment of time, if there is a speech or not. And that's it. So it's just a mathematical algorithm plus some heuristics, no ML at all. And even if you make this algorithm a bit more sophisticated, like WebRTC VAD did, they added some statistical techniques to make it more robust. But still, you can easily trick this algorithm, right? This is the noise in the lower frequency area. And imagine this noise is shifted inside the white box. Then algorithm is completely lost and making the mistakes. So we need something more robust. We need the machine learning here right now. And here comes the deep learning based approach. And this kind of approach is represented by the Celero model. You must have heard of this framework. It's very popular, like outperforming all our VADs. And we can take a closer look now how it works. So basically, it takes the raw audio form and passes on to the convolutional layer block, which extracts like local patterns from it, frequency patterns, energy levels, phonetic characteristics, and so on. And then it goes into the several LSTM blocks, which like learns how these patterns evolve over time. And then the dense layer predicts the probability. And overall, it works really cool, pretty well for distinguishing the noise from the speech, the silence from the speech, and even the background speech from the speech that you want to distinguish from it. And yeah, this model is very fast and nice trade-off between quality and latency, and that's why everyone uses it, and we use it too in our production system. Let me show you how it works. But first, let's make this step from just VAD algorithm onto the VAD-based dialogue management or turn-taking. Here is the pipeline flow, basically, and all the models involved. So ASR generates transcripts, VAD provides the signals if there is a speech versus the silence, LLM generates responses, TDS generates speech. And what is the idea of the VAD-based turn-taking? Basically, when VAD detects the end of speech, you can see on the audio waveform that it's the end of speech. Then we wait for some time to confirm, okay, this is really silence. And then when VAD confirms it, after, for example, 700 milliseconds, we say, okay, this is the end of the turn. We need to switch our state machine to the thinking state so the LLM can generate the response because the user has ended his turn, right? And this is really simple, right? And this approach has a very big flaw. In reality here, we just use the length of silence as the cue to decide, okay, this is the end of the turn or not. And in real conversation, we rely on much richer semantical contextual cues, and like we use a lot more to understand that the user really ended the speech. And that's why this approach is kind of weak. And also wanted to mention the latency. So if we want to provide the answer in less than 2 seconds, and we spend 700 milliseconds on VAD, it's like unacceptable. We need to do it faster and without a lot of false positives, which comes because we use only the silence duration. So we need something stronger. And here comes audio native turn-taking models. And especially the model that we use in our production, it's Smart Turn from PyTorch. So as you can see from the plot, they perform really better than VAD-based turn-taking in terms of balanced accuracy. That's why they do it because they use exactly the same contextual and semantic cues that the humans use in their conversation, like how your pitch falls at the end of the speech, or how the energy drops, or how the rhythm slows down when you really end the turn. And if we take a look at the architecture, so firstly, raw audio form, we are doing the spectrogram out of it, then we transfer it into the transformer model, which is an encoder from the Whisper model that you should know. Like, this is the great model for speech recognition, open source from OpenAI. Basically, we cut the encoder, and this encoder helps us to learn all these local patterns, to learn how the end of the turn looks like in audio. And then we just put on the classifier, which predicts the probability of the end of the turn. And that's why, because we rely on the same stuff as we rely as humans in the conversation, that's why this model works so cool. And also, this is a great trade-off, again, between accuracy and latency. But let me show you how it works in the overall flow. So this is the flow that we have right now in production. And here, we first stream audio chunks inside the pipeline. Then ASR emits transcripts, VAD emits speech states, like user is speaking, speech is stopping, speech is stop. And here comes the nice question: when do we evaluate the Smart Turn model? What is the right moment to do that? And we don't want to run this model constantly, right? It doesn't make sense to run it during the speech because we need to run it in silence. And which part of the pipeline can say, okay, this is silence? Of course, it's VAD that we discussed before. And when VAD says, okay, user is stopping speaking, so I didn't confirm it yet, but I suspect that the silence has started. Please, turn-taking model, evaluate right now. And then the turn-taking model waits for some time, a bit, not to be evaluated on really short pauses in the speech. And then it starts its inference. And after the inference, it provides the probability of the end of the turn. If this probability is higher than a certain threshold, and we have at least some transcript already, then we say, okay, yes, nice. This is the end of the turn. If some condition is not met, then we do the re-evaluation in silence. So the Smart Turn periodically repeats its inference. And even in this case, turn-taking didn't predict the end of turn, we have a fallback based on Celero VAD algorithm. So basically, we do the VAD-based turn-taking as a fallback to prevent our system from being stuck. And after 2 seconds, we end the turn if the turn-taking failed for some reason. And then all the downstream models are starting to produce their answers. So looks nice and solid, right? But this was not always like that, of course. And one cannot just simply create this kind of logic out of nowhere and without stepping on a few rates first. And here on our final couple of slides, I wanted to show you some kind of a post-mortem of our dialogue management development and the lessons that we learned from it. And the first lesson is we need to carefully think how to drive this crazy state machine with a million events happening. And our initial thought was, okay, ASR provided the final transcript, meaning the user has ended their speech. This is the nice moment to evaluate the turn-taking model, right? And we did it, and then we understood that, okay, no turn and was detected at all. What should we do? What is happening? But then we understood, okay, by the time that ASR provided its transcript, a lot of time passed, and we lost this moment where we should evaluate turn-taking model, and we evaluated it too late. And that's why no end of turn was predicted. And lesson 1, let's trigger audio-based model on audio events rather than ASR events. Is that simple? And going to the next lesson, lesson number 2. We need to always wait until at least some transcript arrives, because how we cache those about. We started to notice that assistant doesn't react to some phrases, especially yes or no. Then LLM just got the empty transcript from a turn and was like, what do you want from me? Nothing is happening. And we were like, okay. And when we discovered that VAD plus turn-taking, they work so fast that for short utterances, ASR just didn't manage to provide the transcript in time, and turn-taking model just was forced to end the turn with nothing. The fix is obviously very simple. We just sacrifice a bit of latency in some cases, but we wait for the transcript to arrive. So yeah, the last lesson for me, so there is always a way to improve your dialogue management for your voice agent, because it's a really endless area of research, and that's why it's so exciting to work with that, because you have a lot of stuff to research, you have a lot of stuff to implement, and you always have a lot of stuff to improve that, including naturalness of your speech and at the same time latency. So yeah, thank you. I'm ready to answer your question if you have any. Thank you.